Hi, I'm here with Jamie Garcia.
I am the senior manager of quantum applications and application software for IBM Quantum.
She's here to speak with me about quantum computers, their 433 qubit quantum computer, and how regular programmers like yourself can get a piece of that. So, hi, Jamie. Good to talk to you today.
Hello, great to talk to you as well, Ryan. Okay, sure. So, I am actually a chemist by training. So, I hold a PhD in chemistry and did, basically lab work. Came to IBM because I was very interested in some of the materials science work that was going on there at the time and started doing some research in that space. And during that time, including in my PhD, but also while at IBM, I got to know our computational chemists quite well.
Oh,
I think most experimentalists will tell you if you get a weird outcome of an experiment, one of the first things you need to do is try to figure out why, and that involves a lot of the theory. And so I did a lot of running down the hallway to talk to my computational colleagues to help elucidate what was going on in my flask that I couldn't actually see. So as a part of that process, got very interested in computation as a whole, and the simulation of nature and trying to use computation towards that end. And I think, just from personal experience, realized that there were some real challenges with using classical computers for that. There were certain reactions, for example, we just couldn't look at. I would ask my colleagues and they would tell me it was impossible. And I was like, why?
hmm.
um, so
Like what? Can you give an example?
yeah, actually, some kind of, for me, they were surprising examples, but even like small molecules that were really reactive. So you think of
Mm,
radicals, for example, that you hear about that cause wreak all sorts of havoc in our bodies, but also turns out in batteries too, which I was studying at the time.
right.
And yeah, we just couldn't, the reaction was so high energy and there was so many different things that had to happen with the chemistry that classical computers couldn't model it, even though they were small molecules. So it's just,
Mm,
O2, for example, like
right.
size. So
Right.
anyway, so when I was in Yorktown Heights one day walking down the hallway, I saw one of my colleagues had a poster and it had like chemistry on it, which caught my eye
Hmm.
because you don't see that all that often at IBM.
Right. Right.
Um, and it turns out that he was using quantum computers to study a certain property of a molecule, and it stopped me in my tracks. And I realized this is a whole new tool for chemistry. And so now we've expanded beyond chemistry. Obviously, we're looking at all sorts of different things, but
Right.
I think that was what got me hooked and interested from the very beginning.
Okay. Interesting. So we've talked to a few folks in quantum computing,
Mhm.
but I think it's valuable to kind of get the basics here.
Yeah, so a qubit is essentially our analog to a classical bit. So we use at IBM superconducting qubits. So essentially, these have to be cooled down to like 15 millikelvin. So you may have seen photos of like our big dilution refrigerators that cool our qubits down to that level. But yeah, they're made out of superconducting materials. And what you're doing when you're programming a qubit is you're taking the materials properties of those superconductors and having fixed energy states. You're able to like move electrons into different energy states, and then that basically allows you to program a quantum computer. One of the biggest challenges is keeping them in those states. And I have a feeling we'll
Sure.
talk about that
Yeah. Yeah.
in more
I mean,
detail.
especially since your material science background, like that seems like that's part of the big part of the ball game.
Yeah,
Um,
yeah. But they're fundamentally, it's a kind of different beast too, because we're now using and leveraging quantum mechanics,
right.
right, to really, program the qubits and the quantum computers and be able to perform algorithms on them. So it has a different flavor to it than a classical bit. In fact, you can use things, quantum mechanical properties such as superposition and entanglement, which is those are like new knobs to turn when you're thinking about algorithms. And so it's in many ways and in certain instances complementary to classical devices.
Hmm.
But it really is, it's a whole new thing and a new area to explore.
Right. Um, so talking about the qubits, I've heard that qubits aren't exactly stable.
Great. Yeah.
That you have them super cooled and they're trying to keep them in this particular state.
So, yeah, so qubits, generally speaking, right, like what we're doing when we're programming a quantum computer is we're taking the qubits that are laid out on a chip. So they'll be put on a chip in a certain array, and you'll have, whatever number it is of that. So right now we're still in like single chip tech, regime. So when we're talking about 433 qubits or less, 27 qubits or 5 qubits, what that is it's all on one chip, right? And so when you program them, what you're doing, and a lot of times we leverage 2 qubit gates where you need to entangle 2 qubits together. So you kind of like set it up and map your circuit onto the qubits in a very specific way in order to
Mm-hmm.
get out an answer that makes sense. Now, the stability piece that you're referring to, like qubits are inherently sensitive.
Mm-hmm.
So we have to cool the qubits that we use down to 15 millikelvin because of exactly what you said. You're trying to basically hold the qubit in this state for as long as possible so you can run the calculation that you need to run. And
Mm-hmm.
basically, you have enough time to like perform the gate operations that you need for your circuit. And so I think, they're susceptible to noise. Sometimes we know where that noise comes from, and sometimes we don't. When we think about how we put the qubits and arrange them on the chip, we're doing it in a way that minimizes noise most of the time. So we use what's called a heavy hex, architecture, where essentially what that does is limits the crosstalk between qubits so that you minimize the noise so that you're able to have as long coherence as times as possible, to be able to run the circuits that you want so that you can do a practical calculation, like meaning within hours, not in a lifetime kind of thing. But we've also like developed a lot of other techniques to manage the noise, and this includes certainly like error correction is something that our teams are working towards and developing out the theory for certain error correction that will include having a fault tolerant kind of device available and like error rates low enough that we can actually run some of those codes. But we're also looking at error mitigation, which leverages classical post-processing methods, and sort of is able to capture the noise regardless of whether we know where it comes from or not, but to be able to account for the noise and then correct for it, so that we can get out as accurate results as maybe even in an error corrected regime. So
Hmm.
there's active research ongoing, and then also software tools that are being developed so that we can leverage these techniques as they are developed in real time and then use them for our applications research and running algorithms and circuits
Mm-hmm.
that are interesting to us. So one of the things that we've recently put out, and you can actually access through Qiskit runtime, is something called probabilistic error cancellation. And so what this essentially does is you run a circuit, and then you run like the inverse of certain of the parts of the circuit, and you effectively are able to kind of learn where the noise is that way. And then the post-processing set, it divides it into smaller circuits, and you're able to like basically pull it all back together and account for the noise. So there's opportunities, I would say, for machine learning, certainly, and thinking about how AI and quantum intersect. is another thing that we're thinking very seriously about, especially since we
Hmm.
just announced our system 2, kind of the plans for that, and you can see these quantum centric supercomputer type of arrays and things of that nature. So we're thinking very carefully about like how all these things will play together, and where
Right.
AI can help quantum, where quantum can help AI,
Right.
and what that looks like in particular. Yeah, I mean, it's a tough question to answer, right? Like, so we think of the qubits in terms of, states, right? And so I
Hmm.
think that if you just do like a rough, like back of the envelope type of calculation, people will usually say it's like 2 to the n. So
Hmm.
like 2 to the 433 is a lot, huge.
Hmm. Yeah.
Huge. So in fact, I think if you do 2 to 275, that's like the cutoff for like, that's the number that is like more than atoms of the in the universe kind of style, right? So
Right.
it's absolutely massive.
Right.
But there's a lot of like, nuance that goes into that, and especially when we're talking about actually programming a quantum computer and using it to like look at a like chemistry problem or a problem in finance or anything like that. And in addition to that, you have to, of course, take into account the noise that you have present in the system. So it's hard to say like about what the computing power is of like a device today that has 433 qubits. If you project out and think of, someday we have error rates that are as close to zero as possible, then that's where you start talking about this like 2 to the n and like harnessing the power of the universe and like, all these things. Um, but that's the idea, right? And that's like what we're going for, and the potential that it brings to us in terms of like compute. So that's about what we're aiming for.
And that 2 to the n is computations per cycle.
It's states, right? So
Mm.
it's basis states. So if you look at like, you can use some of the examples of just like molecules, for example. So like water might use somewhere around 14 qubits.
Hmm.
We've actually shown and demonstrated that you can use much less. You can do it with some of these techniques I've been talking about. You can do it on 5 qubits. But regardless, if you have like 14 qubits, then that's like 10 to the 4 classical bits, right? So you can kind of calculate it out that way. But again, there's a lot of nuance here, including we need to carefully consider the types of problems that quantum will be good for. And it's not necessarily like all the same problems that you can think of classical being good for. So I think that's my caveat, but it kind of gives you a rough idea.
Sure. And that's the fantastic lead into the next questions.
Well, yeah, I mean, so again, Shores is an algorithm that is in that sort of long-term error corrected regime, right? That you would need to use error correction for it. And a lot of the famous algorithms that you've heard of that show what we refer to as being exponential speed up with quantum computers, typically what we're talking about are in that regime. And so there's some algorithms that are famous as well for like chemistry, like phase estimation, quantum phase estimation, Shor's algorithms, Grover's. So you can think of, ones that you've probably heard of, needing to have that error correction kind of piece. That said, as I mentioned, we're doing a lot to uh, bring algorithms closer to near term, and error mitigation, and maybe even error mitigation combined with error correction in these early days, will allow us to start solving problems that I don't think like we would have thought that we would have been able to solve before, right? Or as early as this. And so I think like yeah, so Shor's algorithm, definitely again like leverages quantum devices that have these sort of ancilla qubits. So it would be, in general, when you think of like the back of an envelope calculation for what you would need to be able to run Shor's algorithm or like crack RSA or something like that, you'll see numbers that are in the millions of qubits, just to give you an idea, because you have to account for that overhead that comes with the error correction.
Mm.
But the asterisk is we're doing things earlier than we thought. And so I think that that's part of the reason that we're talking about quantum safe now, is that we don't know when things will come, like what the timeline is exactly, but we do have, sort of methods to address this that are available today. And so, for example, in our systems, Z, they are quantum safe systems already, so it's definitely something to start considering now, even though, like, if you had asked me the same question like 2 years ago, I would have just been like, that's so far away, I don't even know. And now I'm like, well, actually, maybe.
Right. Start planning now.
Start planning now, yeah. So we think about it in like three big buckets. The simulation of nature is one of them. So that includes, it's not just molecular simulations, but also like physics fall into this category. Material science falls into this category. There's a lot of richness there, and just sort of the simulation of nature as a whole. And you can think of this as being a space that's interesting because in some ways, nature is quantum mechanical by virtue. And so if you are then leveraging a device that is also quantum mechanical, there's some like real, like obvious connection there. But in addition to that, there's been theoretical kind of proofs that show that we think that there should be at least like more than polynomial speed up possible with using quantum computers to look at certain problems such as dynamics, such as like energy states, ground states, and things of that nature that fall into this category. The second category is basically like generally, mathematics and processing data with complex structures. So this is where quantum machine learning comes in. This is where, we talked about Shor's and factoring. That's where it fits into this category. And, like Shor's, there's algorithms that have been shown or precise things that have been shown for quantum machine learning as well that imply that there should be an exponential speed up possible in certain cases there as well. So, generally speaking, we try to focus on like these two areas in particular we think hold a lot of promise because they do have this like greater than polynomial potential associated with them for using a quantum computer. So it's a real obvious, those are really obvious areas to look at. And then in addition to that, the last category is search and optimization. So Grover's kind of falls into this category. And these are areas that we don't necessarily have those theoretical like proofs yet that there could be, super polynomial speed up or greater than polynomial or exponential speed up. But we know that that it promises probably somewhere around quadratic, but maybe more. We're still researching and looking, and so you never know what you're going to find. So we also have, research in this area as well. And then, in addition to that, there are certain algorithms like amplitude estimation and amplification that we think could act as like accelerators for the other two areas that I talked about. So it's regardless of what kind of speed up we would expect, it could still help, in these other areas as well. So you can imagine the like, it's almost 2 to the n number of use cases that like map onto those areas. It encompasses a lot.
Right.
A lot of different things we can look at, a lot of different areas that we're exploring with partners and coupling it and tying it to like things that are really valuable and hard classically. I mean, that's key, right? If something's really easy classically, like, then, you could argue like, why look at, quantum for it? So something that's hard classically and where we think that quantum can lend some kind of advantage or some kind of speed up in the long run, those are the areas that we're exploring.
Speaking of hypothetical use cases, have you seen the TV show Devs?
No.
Oh, okay.
What was the use case?
Simulating the past and future.
Oh my goodness. Okay. Well, there is prediction, right?
Sure. I mean, simulating nature, right?
Yeah. No, it's not that far off.
Okay. Oh, no.
Yes. So the algorithms, and again, it depends on how you want to use quantum computers, right? So a lot of our discussions are around, like, again, like as we're pointing to like the next generation of these quantum centric supercomputing centers, and where you really have like classical HPC perhaps next to a quantum device, and like how do you best leverage the workloads between those. So I think like there's a lot of things that we've been thinking about in terms of like how you ideally would situate going in with a problem. How would you set it up in such a way that you have like the right parts of the problem being addressed classically, and then other pieces perhaps with a quantum computer. So that's part of it. But the algorithms that we do and the circuits that we run are, inherently different from, a classical. So again, it really comes down to like how you divvy up the problem and which pieces you want to, put where. So I think that's at a very high level what would need to be taken into consideration. And also, something to point out here too is that quantum computers aren't big data type of devices, and so that's another area that again, like we think that there's a lot to be done from the classical standpoint. But if you want to look at something that has high complexity, high interconnectivity, or like is essentially like by virtue dynamic, like those are the kinds of things that the quantum computer handles really well. So but yeah, so if you were to run something on a quantum computer, you want to make sure that it's the right circuit that's going into it, and algorithm that you're using.
Okay, cool. Is there anything else you wanted to cover that we didn't talk about?
Well, I mean, I just think, in general, thinking about the different use cases and the different areas is really important to do as a field, right? So it's not just us, but rather like, this is a very multidisciplinary area, and we need to have folks that are coming from all points of view. So like, whether it's software development, engineering, architects, and thinking, even that are on sort of more of the classical side, learning about quantum and bringing that lens has really like pushed us forward in a truly unique way for this field. And I think it just has to do with the fact that it's an emerging area. And so it's all hands on deck, and we're all kind of learning together.
Yeah. All right. Well, thank you very much for talking with me today, and we'll hopefully you can crack the code and simulate everything all at once.
Well, thank you. Thanks so much today, Ryan.
Of course.